I need a great information?
I think you have to stop share. Okay. Okay, can you hear me? All right, sounds good. This is going to be challenging for me because I like to move around and I'm tethered to the ground here, but we'll do what we can. I can unplug this right here. Can you still hear me? All right. Okay, now I'm not tethered to the ground. Awesome, even better. First off, thank you for the invite to be here. This is a great meeting. I've come many times. It's great to be back. Excuse me having to share. I think the universe may collapse upon itself based on all the sharing we're doing up here, but my talk was crashing Megan's computer, and so they have graciously helped me out. Otherwise, I was going to interpretively dance it for you. So this is probably better. Anyways, Brahim did a great job kicking us off with the importance of relaxers. We've been looking at these things as thin films recently, and hopefully I'll give you a sense of some of what we're up to there. Okay, so before I jump into this, let me acknowledge the folks who do the work. There's a picture of our group back in Berkeley. Lots of great students and postdocs and collaborators there and around the country and around the world. We're always thankful for those folks who pay the bills as well. So as we go through, I'll try to point out folks who are really important. A lot of the work you'll see today is done by my now former student, Jun Kim, who's a postdoc with Chengbao Mom right now. Okay, so probably we don't need to spend much time on what relaxers are. I think this is very clear to this audience, but maybe I'll just throw a few things up here to talk about it. We can make the comparison with ferroelectrics for those who maybe are a little unclear. Right, so in ferroelectrics, we have this kind of classic hysteresis behavior that we think about, and it can be reoriented by the supply electric field in the system. Now, in the relaxers, we have these much more slim hysteresis loops. We have low remnants. We have these randomly oriented polarizations in this system. Likewise, if you look at the dielectric response for the ferroelectric, it's nice and sharp with temperature, whereas for the relaxers, of course, this is a much more broad response. We have these slow kind of dipolar fluctuations inside of these materials. And these are coming about from the fact that you have this kind of nanoscale polar structure inside of these materials, these kind of small, few nanometer in size polarization domains. They can fluctuate in size and shape with time. There's a dynamic sense and evolution to these materials. And they arise from the chemical disorder, random fields, stress and electric fields in the system, all this stuff going on. And people have done beautiful work over the years trying to understand where these things come from. I'm going to give this kind of, a very quick overview here. There's just a competition of these kind of short range and long range interactions inside of these systems that give rise to these. And Ilya's here. He's written some really nice studies on this over the years. And of course, people have looked at how these things respond to different stimuli, right? Temperature, electric fields, pressure, all of these sorts of things can drive these in different ways, right? So we're interested in taking advantage of these sorts of things. Okay, so we started working on PMMPT, kind of the canonical system. We're working at 32% lead titanate, right near the morphotropic phase boundary in this system. And we're growing these epitaxially using barium strontium ruthenate bottom electrodes, and we're growing them on different scandate substrates. These things give us relatively small lattice mismatches with these relatively large lattice parameter materials. And we really were driven to kind of see, one, could you make nice films of these things, and how would the properties differ from what we've seen in the bulk? And ultimately, can you do stuff like what Brahim is talking about with them? Okay, so over the years, we've been making these sorts of things. Here you can see a simple strain series going from relatively small compressive strains to slightly larger compressive strains. Everything looks nice and good. The films grow roughly how we expect them. They are nicely and coherently strained in these systems. We can then do reciprocal space mapping studies where we can look at not just at the Bragg diffraction peaks, but at the diffuse scattering around those Bragg peaks. So it gives us a sense of not just what the lattice parameter is, but also what's the kind of domain structure length scales in these materials. And what we found in this first pass was that as we increase the strain state, we not only change the lattice parameter, but we change the nature of this kind of domain structure inside of these materials. And in general, what we see is that as you increase the strain, you drive up the correlation length, the average domain size inside of these materials. All right, we can also take a look at the properties. We see that as we drive up the strain, we also see a decrease in the overall permittivity, but we see that it remains basically kind of in having this frequency dependent response that we expect for Relaxor. We can get deeply into the different transition temperatures for these materials. For right now, I'm not going to go into this other than to say that, there are some trends, right? As we strain these sorts of things, we see evolution of certain ordering temperatures in these materials. Now, we also did some initial studies of the piezo response for these materials. And what we saw is that, kind of in the intermediate strain state here, we saw slightly enhanced relative to the other ones, piezo response. And, we always want to work with folks who have great insights for these sorts of things. And so I really want to point out Andy Rapp's group from University of Pennsylvania, because they've been very key for us understanding these. So you're going to see these sorts of things from him throughout. And what he's able to do is complete molecular dynamic simulations that help us understand what these domain structures look like, as we hear in this case, going from low strain to high strain. We had this kind of nice sense of how strain is impacting these Relaxor materials. All right, now, stepping back a level, as we started to look at this, we wanted to try to understand, where the responses in these materials come from. And there's been tons of work on this over the years. And so we're just adding another kind of piece into the puzzle here. So if you look back, there's a lot of work that's focused on kind of trying to understand how field induces polarization rotation inside of these and related materials. And there's all these kind of different pictures that you've seen over the years, where we focus in on a single unit cell and how the polarization might rotate inside of this unit cell to give rise to our piezo response. People have even tried to map these sorts of pictures onto the macroscopic strain and electric field responses in these materials. All right, seems all very good. Now, on the other side, folks have also tried to look at how the field induces changes in phase instability and redistribution of these domain structures inside of these materials. This seems very reasonable, right? So when you apply a field, you're going to change the domain structure. And people are trying to pull this from diffuse scattering and other sources of experiments. What we found, however, was that there was never really this done at once in one material, where we take these sorts of things in a single time and drive at the same time and measure both of these sorts of things. And so it's not that people hadn't looked at these, we just wanted to try to put them together. And we wanted to see if we could use the films to do this sort of thing. So can we merge these two pictures and try to get this kind of combined unit cell and domain scale or mesoscale understanding in a single sample at one time? So this is what we've been trying to do. All right, so we used our ability to grow films of these and control the strain state to manipulate them in interesting ways. So the first thing we found from the early work was that when we're in this low strain state, this is on neodymium scandate substrates, we have a mixture of phases, typically the R and MA phase. This gives rise to these nanodomains that have these low angle domain boundaries, and it gives rise to this kind of butterfly-shaped diffuse scattering pattern in the system. Now, if you go out to the high strain state, say -1% strain, here we have a little bit of more of a mixture of the tetragonal and the MC phase. We have a tendency to move towards these kind of larger up and down pole domains in these systems. And we see a change in the diffuse scattering to something that looks a bit like a disk, okay? Now, what we find in the films compared to the bulk, not surprisingly, is that the substrate clamping keeps us from being able to move all the way through all these different steps at once, right? We're kind of limited to just a local area in these things. And what we ended up missing here in this state was the important business that happens here in step B, right? Where we get, the big change in response. So my student had an idea that if you could grow something that was halfway in between these two, maybe you could create a system that was perched right near this instability, and you could have perhaps a mixed, diffuse scattering pattern inside of these systems. So it turns out you can do stuff like this. We can grab samarium scandate and neodymium scandate, and you can get a 50-50 mixture of those substrates, and it gives you a strain state that's halfway in between these two. And when we grow these materials, what we find out is that indeed you end up with both the butterfly and the disc-shaped diffuse scattering pattern in the system, meaning hopefully we've perched this thing kind of in between these two states, going from the rhombohedral MA to the tetragonal MC. And maybe this is where we can get bigger effects out of these materials. All right, so strain gives us access to these intermediate states in these films, which we couldn't just get by driving it with the field normally. All right, now we went to Andy Rapp and his colleagues to try to understand, what's going on, what's the real polar structure of these things look like, and he completed molecular dynamic simulations for us, again, going from the small strain state. This is the in-plane polarization components and the out-of-plane polarization components. Andrew's group can actually simulate the molecular, using MD, the diffuse scattering patterns that we expect for the materials, and then we can compare those things to the experiment. So it looks pretty good. Here we have kind of classical elliptical polar nanodomains like we expect in the system. If you go to the higher strain state in this material, these things have now started to merge in the out-of-plane direction. You can see that they're starting to make these kind of columnar domain structures inside of these materials, and it leads to a smaller and more disordered in-plane polarization in the system. Again, we can have a good comparison between simulation and experiment. And then finally, in the intermediate state here, what we see is something that's got a little bit of a superimposed version of both. So we have, if you look at the out of plane, looks a bit more like the high strain state. But if you look at the in plane, looks a bit more like the low strain state for the system. It has this mixture of these two sorts of things happening. I'm going to, kind of gloss over some of the gory details here, other than to say that we have a reasonable picture of the hierarchical domain structures that exist in these sorts of things, right? So we have these multiple elliptical polar nanodomains, and as we start to apply strain, we start to merge them together, we change their orientation, they start to change. And we'll talk more about how they change as we go on. Okay, now we wanted to see if what we really made looked like these things that Andrew's group was predicting. So we went to Jim LeBeau and his group to do some scanning transmission electron microscopy and polarization mapping to understand these sorts of things. All right, so Jim chopped up the samples, took a close look at what's going on. You can zoom in. Everybody has to have a gratuitous TEM image of their interface. It looks pretty good, and things are pretty nice. All right, now what about the actual structures? So Jim took a look at the end states, right? So low strain, high strain. You can see right off the bat, the colors are giving you a sense of the polarization directions inside of these materials. Here's the color wheel to help you understand. And then we can break it into the in-plane components and the out-of-plane components on the bottom here. So what we see is that as you go from low strain to high strain, there's a merging of these domains. They start to get a little bit larger. You drive these things to come together, and this in-plane disorder that you see in the polarization at low strain goes away in the high strain state. Now, if you look at the intermediate state, again, it's kind of like a mixture of these two things. So if you look at the in-plane here, it looks a bit more like the low strain state. But if you look at the overall structure, it might start to look a little more like the high strain state of this material. Same thing in the out-of-plane direction. What we can see at the end is, and we can pull out a kind of rough estimates of the domain sizes of these sorts of things. So we have something on the ballpark of maybe 4 to 5 nanometers wide, maybe 12 to 15 nanometers long for these polar nanostructures inside of this sample. All right, so, and again, as we strain this thing, what we're seeing is that the out-of-plane polarization becomes dominant as we increase this compressive strain in the system. It never fully becomes ferroelectric, but it does start to have some ordering. Okay, now we can take it one step further and we can try to understand how these things evolve inside. How do the domain structures and the polarization evolve? And to do this, we did a set of in-operando X-ray scattering experiments at the APS on devices that look something like this. So what we do is we fabricate these little capacitor structures with a little offset pad where we can wire bond to them. And then we focus the X-ray in on the capacitor, and we can cycle this thing with an electric field and take the X-ray data as we go. All right, so that's what we do. All right, so we're going to take all 3 of our samples and we're going to carry them through this experiment. So I'm going to show you 2 different types of information. The first is the Bragg scattering. So schematic picture of the diffuse scattering peak with the Bragg peak at the center. Here we're slicing right through the middle of this thing, right through the Bragg condition. And we have, the diffraction condition as a function of electric field going up and back down and so on and so forth. All right, so what do we see here? So for the low strain and high strain states, we see relatively small and smooth changes overall. There's some transformation from R and MA, get a little more MA and then back. Okay, same thing, similar things happening over here. Not a lot of big changes in the symmetry. Whereas at the intermediate strain state, we're going from MA, we see a big transition, a big change in the lattice parameter as it goes from MA to MC in this system. We can extract from these measurements as well of the unit cell lattice parameter an estimate of the strain in the system. And we do see a larger strain coming from this intermediate strain state in the system. Okay, now what about, so that's the local structure. What about the domain structure, the mesostructure? So simultaneous to this, we can also do experiments where we cut not through the Bragg peak, but through just the diffuse scattering of these diffraction conditions. So that's shown here. So again, let's start at the low strain and high strain. So low strain, we cut through these two lobes of the butterfly, and they pretty much exist the whole time through as we go. Likewise, if we have this disc shape to start, it stays constant throughout this process. However, in the intermediate strain state, we start cutting through these two lobes here, and as we increase the field, we actually see increased intensity show up at this disc shape. So as we expected, it's kind of moving towards this kind of structure. Okay, I will note we could do better on this, and this is where people are working on an experimental perspective. These are all line scans. There's a reason I can't show you these same kind of 3D RSM maps of these sorts of things. We don't have that capability yet. So we've only been able to do line scans as we go through here. But from these scans, we can figure out the following things are happening. If you take a look at, kind of a rocking curve experiment here and trace along the diffraction condition along certain directions, we can actually fit these curves with known parameters and figure out what the average correlation length is. And so we see that it goes from about 13 nanometers in the zero field state to something like less than 10 nanometers when we apply a field in the system. And what we think is happening is these polarization units are rotating and the domains are starting to line up and kind of stack themselves on top of each other, almost like a stack of cans in these materials. They're not fully becoming a single domain, but they're moving in that direction. All right, so what we have is basically a lateral contraction of the domains during the elongation of the lattice. And this is evidence of a strong correlation between the unit cell structure and the domain structure evolving at the same time. I don't think there's anything surprising that these things were happening at the same time, but to see it all play out at one side and pull out information about the domain structure and the unit cell at the same time is something we hope we can bring to the table for these materials. So what does this all mean? Well, we can now take the kind of classic picture of strain versus electric field. We can take the classic unit cell picture and the classic domain pictures and really kind of put these things on top of each other, right? So, and start to understand what's going on inside of these materials. Okay, so we've been building out a picture of how these relaxor films respond. And part of this is because there's a growing interest in using these things for applications. Brahim just gave us a great example of one. And there's other things out there. There's lots of nano electromechanical systems. People are interested in capacitive energy storage. We talked about this morning. We've been looking at pyroelectric energy harvesting over the years. And actually, the work that I'm going to talk about now was driven in part by a project we did with Intel, which was looking at trying to create low voltage magnetoelectrics out of these materials. And one of the questions that we had was, is there something like a size effect in relaxor materials? If we were to make very thin, small devices, what happens inside of these systems? And so we started looking at it in a number of materials, but I'm going to show you the PMMPT system here to bring us home. Okay, so what we did is we created a thickness series of the same PMMPT structures that we talked about previously, but using this kind of low strain state that we had before. So we can grow these sorts of things. Here's some X-ray diffraction. Peaks all look very good. Nice Lowy fringes. Everything kind of looks as we expect. If you do a reciprocal space map just in the laboratory, we can prove that all of these films are coherently strained to the substrate. So everything is in the same strain state. And it's effectively bulk-like in nature is what we've seen with this low strain state. Again, Jim LeBeau's group has helped us with TEM, chop these things up, take a close look. Interfaces look all good. It's a nice kind of model system to start looking at what's going on. And remember, this is the sample that looks kind of like the bulk butterfly-shaped diffuse scattering pattern for these materials. Okay, so how do these things differ from, say, a classical ferroelectric? Well, maybe as a just quick reminder, what are the typical things we see in a ferroelectric? Well, as the thickness goes down, we see the domain size go down. We typically see the remnant polarization go down. Coercive field often goes up. And we have a critical thickness of maybe just a few unit cells inside of these materials. So we did temperature and thickness dependent polarization electric field hysteresis loops for all of these things, so you can get a sense of what's going on. And we see a number of different things, which I've kind of summarized here in the temperature and thickness dependent map of the remnant polarization and coercive field, whatever that means for a relaxor material. It's basically the points where this thing crosses the hysteresis. So thicker films, lower temperatures, you have a larger remnant polarization, larger coercive field. So as you decrease the thickness for PMMPT, however, what we see is something that trends towards more linear dielectric response. It does not become more ferroelectric. We don't see it eventually, even though it's strained a little bit compressively, just turning into a ferroelectric system. The remnant polarization goes down, but also the coercive voltage field goes down as well. Below maybe 10 to 15 nanometers, we pretty much don't see any nonlinearity, very, very minimal left over at room temperature in these systems. Okay, so it's a little bit different than what happens in a ferroelectric, and we want to try to understand where this comes from. So we've done a lot of temperature-dependent dielectric measurements to pull out all the critical temperatures that people are interested in. And so I'll give you a sense of this here. So here we go, going from 55, 40, 25, 10, 5 nanometers. You see big changes in the dielectric response as we change this thickness. Now we can summarize all of this. Here is a temperature film thickness kind of phase diagram for what's going on. And we've kind of mapped out, the different critical temperatures. So the Burns temperature, T star, T max, and the freezing temperature for this system. And we have kind of given a little graphic here to help understand what's going on. So at high temperatures, we're paraelectric. We come into this dynamic relaxor phase where we have these dynamic and evolving domain structures. We then keep going into the static relaxor phase. We have a mixture of kind of these more static frozen in domain structures and the dynamic ones. And then ultimately they freeze inside of the system. And what we see is that something quite interesting happens. If you reduce the thickness from 50 to 25 nanometers, you actually first stabilize and enhance the relaxor stability in the system. You see an increase in the stability of the dynamic and static relaxor phase regime inside of this thing. This is also seen if you look at the delta T dispersion. So the change in the temperature related with the frequency dependence inside of these systems for T max. And what we see is that also is maximized here at this 25 nanometer thickness regime. This is kind of a really coarse stand-in for like how good a relaxor is this thing. So it's showing that there's an interesting increase in the relaxor stability, and then it precipitously falls off the cliff after you go past this thickness. All right, so from 55 to 25, Burns temperature, this dispersion temperature difference changes, it goes up, it enhances the relaxor nature and stability. Below 25 down to 5, everything starts to collapse and we're destabilizing the relaxor order overall. Now we can start to go a little bit deeper into these sorts of things. We also fit this data with classic kind of Vogler-Fulcher approaches to understand the frequency and temperature dependent dielectric response. And it falls into kind of 3 categories. So for the 40 and 55 nanometer thick films, they fit quite nicely with the Vogler-Fulcher type relaxation behavior. For 5 and 10 nanometer thick samples, they are not well fit by the Vogler-Fulcher. It's much more of a Debye type relaxation in these materials. And for the 25 nanometer sample, it's kind of fit by both. It's kind of somewhere in between these 2 types of responses overall. Okay, so there's something like a dome-shaped instability region for the relaxor behavior. But what we see is that as the thickness approaches the polar domain size, this relaxor state starts to crumble. That's perhaps not too surprising. But we wanted to try to understand a bit more at the nanoscale how this was happening. All right, so again, we did this temperature-dependent X-ray diffraction experiments to pull out information about the domain structures in these materials. And so what I have here is temperature, and again, thickness dependence, and we'll show you the diffraction patterns that we see for these systems. So at room temperature, what we see is that as you decrease the thickness, the diffuse scattering weakens. So you go from thick films to thin films, scattering goes down. Now, if you look at both high and low temperatures for these systems, what we see is that if you go to high temperature, it weakens the diffraction intensity, in particular for the diffuse scattering. So this one is a nice one to see. Nice robust diffuse scattering, and it goes away, and it increases the intensity as you go down. So everything kind of makes sense here. But what this allows us to do is start to pull out some temperature dependence for these sorts of things. So we have now the average correlation length as a function of temperature. And what we see is that the correlation length or the domain size goes up as the temperature goes down in these systems, but they do so at different rates. The thicker films are different than the 25, and we don't have anything to fit for these thinner ones. We can actually use this data to try to get a kind of rough estimate of what might be the critical thickness for relaxor stability. We only have a couple points here, but you can guess something probably in the ballpark of 5 to 10 nanometers for these systems. Perhaps this helps explain why we don't see any real switching happening in these thinner films. And again, for the 10 and 5 nanometer thick films, there's no diffuse scattering even down to the lowest temperatures that we've checked at in this system. Okay, now we can look a little bit further to try to understand what's going on. And what we see is that there is an enhancement of the polarization fluctuations, which we believe is driving the reduction in the polar domain size with temperature. We can pull this out from the diffuse scattering in the PE loops using Arrhenius fits of these sorts of things. And it's consistent with what we've seen for the freezing temperatures before. And so we have this kind of temperature dependent evolution of the polarization fluctuations in this system. All right, now the question still remains, however, what's up with this, trend in the Burns temperature? Why is it, changing around 25 nanometers? And so we really wanted to understand how the domain evolution is happening in these things as well. So we needed this real space characterization. So again, we went back to Jim LeBeau's group, and they helped us take a look at these sorts of things. So I'm going to show you 3 types of data here for these samples: combined polarization, the out-of-plane polarization, and the in-plane polarization for these systems. All right, so start with a thick film, 55 nanometers. Jim has done his studies. So this is the overall polarization structure, the out-of-plane and in-plane components of these things. What do we see here? Well, when it's much thicker than the polar nanodomain size, we see these low-angle domain boundaries. They're typically on these kind of 011 type directions. And we see that these things are anisotropic. They're a little bit longer than they are wide. And if you just kind of do a Fourier transform of what's happening here, you have a random distribution of polarization vector. So randomly oriented polar nanodomains. Now, if you do the same thing for a 25 nanometer thick film, okay, now we see that things start to change quite a bit. So now we're approaching kind of the length scale of the longer dimension of the polar nanodomains. What we see here is that the domain structures start to get a little bit larger, a little more out-of-plane correlation, and also in-plane correlation in these systems. So we have something that looks more like a largely horizontally aligned polar nanodomains stacked along kind of this 001 out-of-plane direction of these systems. So you have some preferential alignment to the polar nanodomains, which shows up in this Fourier transform of the polarization. We think this explains, why this is turning down. And basically, we're freezing out the polar nanodomain reorientation. So let me just bring us home here. We've looked at this in the phase field. We see similar sorts of things. I'm going to give Andy's stuff a little not enough attention here. But then, oh, sorry, I went too fast. And then I'll just leave up the conclusions here. So basically, we've been trying to use the thin films as a way to take a deeper look at these kind of relaxor materials, understand what's going on, and see if we can kind of help out using these sorts of things in real applications going forward. So thank you for your attention. I'll be happy to answer any questions.
Any questions?
These structures you have some solutions with different, different possible local watering. So I don't know how it's possible to control that, but I'm wondering, for example, how reproducible it is to make films or something like this. You get exactly the same behavior, or maybe have a change depending on the local watering situation. I can follow up question that is that something that you can get external direct information on, like what the correlation of your neighbors is, or whatever.
Yeah, it's a great question. It's something that we worry about. So I'll try to break it into different parts. So one, if we change the growth conditions, in particular, we have a temperature series and things like this, we do see changes in the manifestation of that order and also the properties that we get out of these sorts of things pretty dramatically. So here we're trying to use what we think are the optimized conditions. From both the MD simulations, we've been looking for what would happen if you had different types of local chemical order and how that impacts the properties. But we've also, from the TEM, been able to look for these sorts of things. So we've specifically looked for that local ordering. So in the films I've shown you here today, we don't have it, but you can get that to happen. What we're doing is taking it one step further. We're actually creating artificial superlattices out of these kinds of materials where we specifically order them along different directions at a few unit cell length scales as kind of the ultimate manifestation of what you're saying. And what you get is crazy anisotropic properties. You'll get like relaxor behavior in one direction and something that looks ferroelectric or in some cases dielectric in the other direction. So that is a very interesting design approach that I think is quite productive.
Yeah, thanks, Nick, for seeing really interesting results. I wondered your operando XRD, well, if you look at quite small capacitors, but huge side.
Yes.
Have you tried new cycling? Is it an evolution in the correlation bands?
Yep. Yeah, so the way that's a great question, by the way. So the way these experiments work is we don't get them in one shot. So we're doing these things at typically in the kilohertz frequency ranges. So, and we often have to do many, many cycles at each field to get sufficient data, and then we average those things. So even within that data that I showed you, it's millions of cycles of these sorts of things. So we have not seen, and we've done kind of like fatigue-based experiments on these sorts of things. Like, is there a big change? Do they start to coarsen and never come back? We have not seen that in the low strain state films. Yeah. Yeah. Sorry, I was too slow.
The regions with
Yeah. So what we think is happening is that there's a strong tendency to push the polarization in plane when you make this thing thinner, right? So as soon as it hits kind of a critical length scale, so these things are like long elliptical structures. They're maybe 5 to 7 nanometers across ballpark, and they're maybe twice as long or something like this, maybe sometimes 3 times as long. As soon as we start to hit that point, you restrict their ability to adjust and reorient and change their properties, because now they're just running into the edge of the film. And at the same time, the depolarization effects are probably turning on, driving the polarizations more in plane. So it's kind of stiffening up that polarization. That's kind of how we're thinking about it. So the chemical, the chemical and valence random fields are still there, but it's fighting against these other energy scales that are coming on. So it still wants to be a relaxor. It's never turning fully ferroelectric, but it's not having this same kind of, disordered polar structure that we see before. So those boundary conditions are doing something that force it into that direction.
Yeah, let's think on them. The next talk is going to be given by Professor Newton from Media Research Laboratory, and the title of the talk is towards high-speed dynamic control of optical properties and effective electricity in glass.